So now that we've talked about the interface and of completion service and the executor completion service class, let's take a look and see how we can apply this to our ongoing PrimeChecker app. And you'll see both how the PrimeChecker uses the executor completion service, and we'll also see how it's used that MemoiZer that we had talked about recently in order to be able to transparently optimize the results. So this app is the same app as before. There's no real difference to the app. It's checking to see if n random numbers are prime and large random numbers are prime, so that's the same as before. It's embarrassingly parallel. It's compute bound. That's the same as before. It uses the PrimeCallable class just like it did before. Just to be fun, this time we use an executor service that has a cached or variable size pool of threads. The last one we used the fixed size pool of threads. That was the executor service implementation we looked at before. This one's, just to be a little different, uses a cached pool of threads. And what will happen is, as you start running these requests, it'll spawn a thread for each new request, which actually could be a lot of threads. So if the computations run very quickly, the threads will be recycled. But if the computations are prime and take a long time to run, it'll keep spawning threads. So it's actually probably not the best thing to do is to use a cached thread pool. I just did it just to show you how to do something a little different. Here's the PrimeCallable class. We saw this before. This is really pretty much unchanged. PrimeCallable implements callable, so it's going to have a call method. It has a function that is passed in here. Keep your eyes on this function. It's like a magic show. So this function that's passed to PrimeCallable is a function. And then when we come along and we use the MemoiZer, this will still be a function, but it'll actually be implemented by the MemoiZer, which has this special transparent caching capability that's added. Here's the call method. This is the hook method that's used to essentially apply the function on the prime candidate. So whatever that function happens to be, whatever that processing is, that's what will get called. This is what's actually a little different from the previous implementation, which hard-coded the call to is prime, so it was hard-coded, so this is not hard-coded. And then the result that comes back here will indicate what happened. Did that prime number candidate actually end up being a prime number or not? Okay, so that's more or less what we had before. It's not identical because we have a function this time, so that's a little different. And that function calls whatever the function is that's passed in as a parameter. But otherwise, the logic is very similar. Here's how we connect the MemoiZer to all this stuff, and it's really neat. So remember the MemoiZer, we talked about that before. That's what we used in order to be able to transparently optimize these primality checks by caching the results of previous checks or memoizing them. People sometimes joke that memoize is what Elmer Fudd might say for memorize, memoize. So the memoizing cache is used in this stream of PrimeCallables. And this, again, will have a little bit in common with what we have seen before. So when a person starts the computation, this method gets called. And you can see what it does is it creates a MemoiZer, which caches the results. And this MemoiZer is going to use, in this particular case, the brute force checker and a new concurrent hash map. It turns out to be very easy to switch this around, though. If you don't want to use a brute force checker, if you want to use a more optimized checker, all you have to do is just change the method reference that is passed when you create the MemoiZer, and then everything else we see below will transparently work with the new implementation. We start by generating a stream of count random numbers that are going to be very large, and there'll be duplicates intentionally so we can get the benefits of caching. We then go ahead and create a new PrimeCallable, passing in this random number that was part of the stream, and our MemoiZer. So remember, the MemoiZer is going to transform these random numbers into PrimeCallables. This MemoiZer is going to transparently cache the results of the prime checking, because that's using the brute force checker. Notice how this MemoiZer can be used wherever a function is expected. In particular, if you take a look here, you can see that PrimeCallable, which is what this guy is, expects to have a function. So originally we were passing in Or we could have just passed in brute force checker if we'd wanted to. But by doing it with a mMemoizer, then we can do the brute force checker only when we don't find, or this implementation will do this only when it doesn't find that random number already in the mMemoizer's cache. But the key point, so this question had come up last class when I talked about mMemoizers. The key point here is that this can be used transparently wherever we expect a function to be used. So this could either have been brute force checker directly, or we can encapsulate the brute force checker in a mMemoizer and then use the mMemoizer as if it were a function because it implements the function interface. And then the last thing we do is we take this stream of PrimeCallables and we submit each of these to the executor completion service. So that's the submit call. And you'll notice some interesting things here. You'll notice that unlike the previous example, the one that was the executor service one where we were creating a list of completable futures that came back from submit. If you go back and look at the code, you'll see that's what we're doing. In this case, we don't need to do that because all that machinery for keeping track of the futures is actually done by the executor completion service. And so all we need to do is just run a for each loop here. So for each PrimeCallable, we're going to submit that PrimeCallable to the executor completion service. So that's a lot cleaner because there's no need for us to explicitly keep track of the futures and then have to go off and write the code to process them in a synchronous future processing model. Okay, so that's the key part here. That's the submission part. So we have one thread submitting a bunch of work to a pool of threads, which then run in the background. We got to find some way to get the results back, of course. So what we're going to do to get the results back is we're going to make something called a completion runnable, and I'll talk about completion runnable in a second. And this is stored actually in retained state, so we can save it when a person rotates the phone. This doesn't get blown away. We create a new thread, associating it with that runnable, and then we start the thread. So now the thread is running in the background. So we have a background thread waiting to process the results of these asynchronous computations. Here's the completion runnable class. You can see it implements runnable. So when we start it, that will run. Here is the run hook method. The run hook method iterates through all the expected results, and that's just the number of prime numbers we're checking. So we go from 0, 0 less than m count, which is the number of numbers we expect. And what we do at every step along the way is we go and we say, hey, executor completion service, please block until there's something for me to deal with. So this background thread is saying, please block until there's a future that's completed. And notice that it'll be when take returns, we know we've got ourselves a completed future because that's its whole purpose in life. You don't get anything back from it until there's something there. So what will happen here is that take will block until there's a future, but once take returns a future, the get method won't block because it's already been completed. Otherwise, it wouldn't end up in the queue. So that'll keep running until everything's processed. And then we're going to go and, as we do this, we're going to take the results and process them somehow. And then we're all finished. We'll say we're done. Retained state is this object that's used in Android to make sure that when runtime orientation changes occur, we don't blow away our concurrent objects, our objects that are running concurrently. And you can see there's a bunch of them now. We have an executor completion service. We've got an executor service. We've got a completion runnable. We've got a thread. And we've got a mMemoizer. So these are all things that we want to live throughout the processing of the computation. So we don't want those things to go away when the runtime orientation changes. And this is just the magic in Android to restore and or save that special configuration state. You don't have to worry too much about that at this point, but that's what's happening in Android. Okay, so that's the end of the discussion of the example that applies the executor completion service and the mMemoizer to our PrimeChecker app.